The Joint Quantum Institute was formed around 2006, if I'm remembering correctly, to combine the expertise in condensed matter physics among people who are interested in quantum phenomena and the expertise in atomic physics of people who are also interested in quantum phenomena. And by quantum phenomena, we mean things where quantum coherence is important, where quantum entanglement is important. The world is quantum. Everything is quantum. But there are some things that are more quantum than others. So things that rely on quantum coherence, the coherent superposition of different quantum states, on entanglement between different quantum systems, these are the things that we focus on in the Joint Quantum Institute. And the important feature is that we're focusing on them both from the point of view of condensed matter and the point of view of atomic physics. Well, one of the things that is a particular focus of the work that we do here in the JQI, as well as the work that we do here in my research group, is to use atomic systems, sometimes other kinds of systems like photonic systems, to simulate the behavior of quantum systems described by simple, iconic Hamiltonians. Hamiltonians that are often used as simplified models for example, condensed matter systems, but are nevertheless very difficult to calculate directly. We can use our atomic physics systems, or sometimes photonic systems, as I said, to simulate that quantum behavior and get information that would be difficult to get otherwise. So what's a Hamiltonian? A Hamiltonian is the thing that describes the physics of some kind of a physical system. Basically, it's a way of expressing what the energy of a system is in terms of, say, its kinetic energy, its potential energy, being in some kind of a trap, or some kind of a periodic potential, as an electron would experience if it's in a crystal. There'd be some kind of a periodic potential. Our atoms experience such periodic potentials when we interfere laser beams to make standing waves. Then the atoms experience that kind of periodic potential that's part of the Hamiltonian. But the hard part of the Hamiltonian is when the atoms or the electrons interact with one another. That's the thing that's really hard to deal with when you're trying to ask, what will this system do? Photonics, in the sense of using light, is at the basis of essentially everything that we do in my laboratory. That is, we use lasers to manipulate atoms. We use lasers to store and control atoms. We use lasers to create the Hamiltonians, the basic physics that we want to study. So light is at the heart of essentially everything we do. On the other hand, when I think of photonics, there's another sense in which I might think of it. For example, one of the things that we can do is we can create, for example, a two-dimensional system of atoms and ask, how does this two-dimensional system behave? We can also create a two-dimensional photonic system, that is, a set of optical resonators. When I say we, I mean other people in the Joint Quantum Institute. A set of optical resonators arrayed in 2 dimensions, and then inject light at one edge of this photonic system, this array of resonators, and see how that light propagates throughout this 2-dimensional array. It turns out that such a photonic array can be used to simulate the kind of behavior you see in something like a quantum Hall system in condensed matter, where electrons are the things that are the carriers of the motion, so to speak. And the fact that you can do this with a photonic system gives you a different platform in which to study 2-dimensional physics. And so, over a period of time during the early 1980s, we developed the technique for slowing down an atomic beam of atoms. So you got a stream of atoms going one way, we got a laser beam going the other way. It's not so easy to get those atoms to absorb tens of thousands of photons, but we figured out how to do that over a period of years, and got to the point that we could slow down a beam that starts off at hundreds of meters per second, slowing it down to tens or even a few meters per second, and then trap it. And that was the work of the early 1980s. Then we worked on continuing to cool the atoms by, after having slowed this atomic beam down and having the atoms going at quite modest velocities, meters per second, then bringing in laser beams from all different directions to continue the cooling process down into the velocity range of centimeters per second. Now, one of the things that was really exciting that happened during that time in the late 1980s is that we had a theory that would describe quite simply and straightforwardly what the temperature would be that you could get that arose from the balance between the natural heating processes, the randomness of the atoms absorbing and emitting photons, and the preference for absorbing photons from laser beams that are opposing their motion. That balance produces an equilibrium temperature, which was, according to the theory, incredibly low, a few hundred microkelvins. And what we found in the late 1980s was that the actual temperature was tremendously colder than what the theory predicted. Now, this was fantastic because the whole idea was to get the atoms as cold as we could, and we had apparently gotten the atoms colder than we could, a huge violation of Murphy's Law, and something you don't often find in the laboratory. Eventually, with the help of other colleagues in the field, like Claude Cohen-Tanuji and Jean Dalibard in Paris, Steve Chu and his colleagues at Stanford, came up with a theory for why this was so. It was because we had, as a community, had oversimplified our understanding of what was going on with this process, and it needed to include more stuff, and when they did, then it explained why the temperatures were so much colder. And then, guided by that new understanding, we were able to get the temperature of cesium atoms, for example, down below 1 microkelvin, when the theory would have said they couldn't go any lower than about 130 or 140 microkelvin. So something like 200 times colder than what the theory said was possible was what we were able to get with a gas of cesium atoms. Now, cesium was really important because cesium was and still is the atom that is used to define what we mean by time. And one of the duties of NIST is to keep the time standards for the country. And we do that by making atomic clocks using cesium. Well, now that we had cesium down to a temperature of below 1 microkelvin instead of a temperature of 100 degrees C, about maybe 400 Kelvin, you could make a much better clock. And today, the best clocks, which are in Boulder, Colorado, keeping time to a part in 10 to the 16, a part in 10 to the 16, that's a second in 300 million years, and in similar standards laboratories around the world. All of those places are keeping time with laser-cooled atomic clocks. So it's completely revolutionized timekeeping. But that's just the beginning. People like Dave Wineland using a single trapped ion and laser cooling it, and using optical frequencies. So optics comes in again. You cool the atoms, and then you look at an optical transition and measure its frequency directly. He's gotten down into the parts in 10 to the 18 level. His colleague Jun Yi, also out in Boulder in our NIST laboratories out there, trapping neutral atoms similar to the way we trap things here in optical lattices, that is in an interference pattern of laser beams, getting down to about 2.5 times 10 to the minus 18, which is 1 second in the age of the universe. It's completely revolutionized timekeeping, but that's just the beginning. It's completely revolutionized atomic physics, and it's completely created an interface between atomic physics and condensed matter physics because of this idea of optical lattices and cold atomic gases simulating or emulating the behavior of electrons in condensed matter systems. What we want to do is to make them move a whole lot slower. So the first thing we do is we come in with a laser from the opposite direction and shine that laser up the throat of the atomic beam so that it is directed in the opposite way to the way the atoms are going. The atoms absorb the light, and after having absorbed a sufficient number of of photons, which is on the order of tens of thousands of photons, the atoms slow down to a crawl. And then we go to the next area of the apparatus where we trap the atoms, again using laser beams coming in from all the different coordinate directions, along with some specially configured magnetic fields. We can both trap and cool the atoms down to temperatures that are on the order of microkelvins, microdegrees above absolute zero, and trapped in a volume that's on the order of a cubic millimeter. Then we transfer those atoms to another kind of trap that is more benign. What do I mean by benign? Up to this point, we've been scattering photons off the atoms. They've been absorbing photons, they've been emitting them randomly, and there's been a balance between the heating process that comes from the randomness of that photon emission and absorption process and the cooling that comes from the momentum transfer of having the atoms preferentially absorb from laser beams that are directed in the opposite way that the atoms are moving. Well, at some point, we get as cold as we can that way, and that is on the order of microkelvins. Then we want to go further, and again, we're often using lasers. Sometimes we're using magnetic fields, but sometimes we're using lasers to trap the atoms, but now without scattering photons from them. That is, without any spontaneous emissions, which is to say without any heating. And then we continue the cooling process by allowing the most energetic of the atoms to escape. We call this evaporation, because it's just like what happens when you want to cool your coffee. You blow on the coffee, the most energetic water molecules leave the surface of the coffee. What's left behind is obviously lower energy and therefore colder. That's how cooling your coffee works. Same thing here, except we get down to nanokelvins of for our temperatures, just a few billionths of a degree above absolute zero. And at these low temperatures, assuming the density is high enough, something wonderful happens. These rubidium atoms undergo a phase transition from one sort of a gas, what we might call an ordinary gas, to a remarkable gas called a Bose-Einstein condensate, where a large fraction of the atoms are in the lowest state of motion that quantum mechanics allows them to be. And that's as far as we can go with atoms, is to have them in as low a state of motion as quantum mechanics allows. Now, some fraction of them aren't in that state, and we try to get rid of those as much as we can to try to get the temperature of this gas as low as possible. And that temperature is on the order of nanokelvins. And then with that, we can do interesting physics experiments.
Now, the first Bose-Einstein condensate of an atomic gas was made in the NIST laboratories in Boulder, Colorado, by my colleague Eric Cornell. He and University of Colorado physicist Carl Wyman used a combination of laser cooling and evaporative cooling to Bose-condense a gas of rubidium atoms in 1995. Wolfgang Ketterle and his group at MIT followed that with a condensate of sodium atoms, and in 2001, the three of them were awarded the Nobel Prize in Physics for that work. A few years after that, Debbie Jin, also of the NIST laboratories in Boulder, made another huge advance and another triumph for optics by upgrading the cooling techniques to cool a gas of fermionic atoms. One reason this was so important is that among the two kinds of particles in the universe, fermions and bosons, electrons are fermions. And if you want to learn about how electrons behave in materials, it's a good idea to study how fermionic atoms behave in optical lattices. Debbie Jin died in September of 2016 at the age of 47, having created a research direction that has inspired activity all over the world. And all of us in this community are missing her and grieving her loss.
Had we not taken a basic research approach to what we were doing, we never would have discovered the key features of laser cooling that allowed us to make the atomic clocks that are ubiquitous today. So this combination of being motivated to some extent by the possible practical applications, but taking an approach that says, I want to understand the most basic features of the science behind what I'm doing, that combination is the thing that made it work.